Okay, so in this podcast, we're going to talk about how to balance chemical reactions. Okay, so first, we can't really talk about balancing chemical reactions without mentioning the law of conservation of mass. So, the law of conservation of mass states that matter cannot be created or destroyed, only rearranged. So, in a reaction, basically what that means is that we must start and end with the same mass. Even though the substances may be different and have different properties, the mass has to remain the same. All right, so why do we need to balance equations? Well, the whole reason we balance equations is so that they satisfy the law of conservation of mass, because that's what happens in real life. So I want you to look at my example on here. So I have this equation over here where hydrogen and oxygen are making water, and this is an unbalanced equation. So down here I totaled up how many hydrogens, oxygens I have on the reactants and how many I have on the products, and then I also have a picture here. Hopefully you'll see that we don't have the same number of oxygens, so it's like we destroyed an oxygen, but we know that can't happen. So what really happens is we get two H2s reacting with one O2 to make two H2Os. So you see when you count your atoms this way, because it's a balanced equation, this is how the reaction actually occurs. Now we're satisfying conservation of mass. So the only thing that's different are these little numbers in front, these little subscripts. So that's what we need to do in order to balance, is we need to put little subscripts in there. All right, so for you guys that like steps, here's a step-by-step guide to balancing. You're going to write the unbalanced equation, count the atoms on each side of the unbalanced equation. Then we're going to add those coefficients, the big numbers in front, to make our number of atoms of each type equal on each side. Realizing that the coefficient in front times a subscript on the formula of the substance is going to tell us the number of atoms. If we can, we reduce our coefficients to lowest possible ratio, and then make sure you double check so you get it right. All right, I also wanted to throw some helpful tips in here to you. Always balance just one element at a time. Don't try to balance more than one or you get confused and it just gets crazy. Make sure you update all your atom counts after you put your coefficient in front. So when you put that coefficient in front, make sure you go down there and update how many you have. If you have an element that appears more than once on one side of the equation, you want to balance it last. And then lastly, I prefer to balance polyatomic ions as a single unit, and I will explain this process to you in just a second. All right, so here's our first example. So first step, hopefully you remember, is that you need to do an atom count. I like to do everything as simple as possible. So I like to write my atom count down the center, and then over here I'm going to write how many I have for the reactants, and over here I'm going to write how many I have for the products. So I have 1 aluminum and 2 nitrogens on the reactant side, 1 aluminum, 1 nitrogen on the product side. Okay, so hopefully you see that I have my ends don't match up, right? I have 2 on one side, 1 on the other. So what could I put in this coefficient spot over here to give me 2 ends? Well, hopefully you were thinking of 2. Now, because N is also attached to Al, Al also is 2. So come down here and update your atom counts. All right, now our Als aren't balanced. So now I need to have a 2 in front of my Al. So I'll have 2 Als. Now N, we don't need anything in front of this N2 on this side, right? Because we're balanced at this point. But understand there's like a little imaginary 1 over here. I can't draw an imaginary 1. There we go. All right, let's look at another example. All right, so write your atom count. Count how many you have on each side. Okay, so I see that I have 2 aluminums. So I need 2 aluminums on this side over here. So I'm going to put a 2 there. So now I have 2 aluminums. Okay, and then my oxygens, I've got 2 and 3. Well, how the heck can I get 2 and 3 to be the same number? Hopefully you're thinking, well, the only way I could do it is 2 times 3, right? So 2 times 3 gives us 6. So if we take them both to 6, it'll be balanced. Okay, so on this side, what times 2 down here is going to give me 6? Well, hopefully you said 3, because 3 times 2 is 6. All right, then over here on the oxygen side, we've got 3 of them. So a 2 in front would give me 6 oxygens. Now, this also affects my aluminums, so now I have 4 of those. Oxygens are balanced, but now my aluminums aren't again. So the only way for me to fix aluminum is to cross out this 2 and make that a 4. Okay, and another example. So we got P and O. 1, 2, 2, 5. All right, so I need 2 P's on the first side, so I'm going to put a 2 in front. All right, now I need my oxygens to work out. Okay, again, you know, how am I going to get 2 and 5 to be the same number? Well, the only way to do it is to take them both to 10, right? So if I put a 5 there, it gives me 10, and a 2 here gives me 10. But again, that 2 changes that P, because 2 times 2 is 4. And then now my P's on the other side are messed up, so cross that out and put me a 4 over there. Okay, all right, on this one we've got K, Cl, and O. So I've got 1, 1, and 3, and then 1, 1, and 2. So I've got to get my 2 and 3s to be the same number, so I need to take them to 6, right? So if I put a 2 there, that changes my K's and my Cl's, and then now my O's are 6. Now, I wanted my O's 6, so I need to put a 3 over here. So that gives me 6. And now I got to fix my K's because they got messed up. So I've got 2. So if I put a 2 there, I'd have 2 K's and 2 Cl's. Ta-da! It's balanced. All right. If you're balancing a reaction that contains a polyatomic ion, if the polyatomic ion appears on both sides of the equation, then you can count it as like its own unit when you're balancing, and it'll simplify things for you just a little bit. All right, so here's an example. So hopefully you see we have the polyatomic NO3 and the polyatomic CrO4. So when you're writing your atom count, write that entire polyatomic all together. Okay, so now we count. So I got 1, and I got that 2 outside there, right? So I got 2 NO3s, 2 Ks, and then CrO4, it didn't get parentheses around it, so that means I only have 1 of those. All right, on PB side, on the right side, PB, we got 1, NO3, 1, K, 1, CrO4, 1. Okay, so I need to get 2 NO3s on the product side. So if I put a 2 in front of that term, that changed my K's to 2 and my NO3s to 2. Bam. All right, another example, we have, hopefully you see the polyatomic NO3. It's on both sides. And you see this OH, again, on both sides. So when I make my list, I'm going to count them just all together. Okie dokie, so I got 1 Ag, 1 NO3, 1 Na, 1 OH. All right, and then over here I got 1 AG, 1 NO3, 1 Na, 1 OH. So guess what? This equation is already balanced. So when it's already balanced, remember it's just a bunch of little imaginary ones there, okay? I don't know why I can't draw an imaginary one. There we go. Okay. All right, and last example. So there are several polyatomics here, okay? So definitely got some NH4s, right? We got some SCNs, okay? And then I see an OH here, but is there an OH on the reactant side? You might not think there is, but a little trick is that water can be written as HOH, in which case you do have an OH. Also realize that you have these just regular H's. So you got to make sure that you're careful when you're counting this. You also got H's in the NH4, right? There's just H's everywhere. So make sure that you are paying attention when you do this. All right, so I got NH4, SCN, H, and OH. All right, so I got one NH4, one SCN. All right, and remember I'm looking at this formula, so I got one H and one OH, one NH4, one SCN, one H, and one OH. Well, guess what? That one was balanced again. Yay!